Yeah, thanks for the introduction and thanks to the organizers for giving me the opportunity to talk. So I'll start by giving a very quick introduction to the basic definitions in condensed mathematics before giving a little tour of that part of Mathlib and a few new things that are hopefully on their way to Mathlib soon. So I guess condensed mathematics is familiar to lots of people in the Lean community because of this liquid tensor experiment. And then we had a workshop in Copenhagen last year, which was, I guess the goal was to sort of get the basics of condensed mathematics into Mathlib, and that went very well, and we have quite a lot already. Yeah, I'm very thankful for all the efforts of the people involved in LTE and also the participants of the workshop in Copenhagen for all their work on this. Now, so the building blocks of condensed sets are these topological spaces called profinite spaces, and they're just compact Hausdorff spaces which are totally disconnected. And totally disconnected means that the connected components are singletons, but in this context, it's equivalent to any two distinct points being, so you can separate them by Clopen sets, which is a much more understandable condition than totally disconnected. But a convenient way to think of them is also as co-filtered limits of finite sets, and these descriptions are in fact equivalent. On the category of profinite spaces, we can define a Grothendieck topology called the coherent topology. So a Grothendieck topology is just some structure we define on the category saying that some families of maps are covering families. And in this case, the coherent topology is just finite families which are jointly surjective. So like actual covers, finite covers. And a Grothendieck topology is exactly the structure you need to define what sheaves are on a category. So that's what a condensed set is. It's a sheaf for this Grothendieck topology on the category of profinite spaces. It has a much more explicit description. If you don't want to think about Grothendieck topology nonsense, you can just think of it as a contravariant functor to sets, which preserves. So yeah, if you think of it as a functor from the opposite category, you can say that it preserves finite products, but what it really means is that it takes finite disjoint unions of profinite sets to the corresponding product. And for a surjection of profinite set, this induced diagram is an equalizer diagram. So yeah, we call this the equalizer condition. Yeah, so the point of condensed set, or the idea, is that they should generalize topological spaces in some way. They form like a better behaved category than topological spaces. And there's a functor from topological spaces to condensed sets, which is given by just mapping into that topological space from profinite sets. And this functor is fully faithful when you restrict to so-called compactly generated topological spaces. So all reasonable topological spaces. Okay, but some of you may have noticed a problem with this definition here. So when you talk about sheaves, you would like to be able to sheafify, and that's impossible when your sheaves are defined on a large category. I mean, I won't go into detail about the definition of sheafification. It involves something called the plus construction, which is a co-limit defined over a category which has basically the same size as the defining site. Oh, so a site means the category equipped with algorithmic topology, for those who don't know. And this is a problem. So we need to modify the definition of condensed sets a little bit. And sheafification is supposed to be just it's a left adjoint to the inclusion of sheaves in pre-sheaf. So you take a sheaf, you take a pre-sheaf, and you get like the universal sheaf that it maps to. Okay, so the first solution to this problem proposed by Clausen and Schulze is to consider these uncountable strong limit cardinals. And this just means that all smaller cardinals have the property that their power set is also smaller. And this means that when your objects are kappa small, then you can perform all the sort of usual constructions, take power sets and products, and stay below that cardinal. And then you restrict your sheaves to kappa small profinite spaces, and then you take the co-limit over the poset of these cardinals of these categories of kappa condensed sets. So a condensed set is an object of a co-limit of categories. And the way people do this is that they say this sometime at the beginning, and then they just say, we won't care about these set theoretic issues and just pretend that condensed sets are sheaves and not objects of some co-limit of categories. And of course, this is a terrible solution for formalization. Now, this theory was developed sort of in parallel by Clausen and Schulze and another pair of people, Clark Barwick and Peter Hain, who called it pycnotic sets. And they used a different solution, which involves universes. And the easiest way to explain that to this crowd is just by showing the lean code. So this way we just make our sheaves take values in a category of bigger sets somehow. So it's a sheaf for the coherent topology on U small profinite spaces, taking values in U plus 1 small sets. And like actually Lean's universes make this very, very convenient and yeah, so this is a very convenient solution for us. Now, there is a third solution, which is to just avoid the problem and talk about something slightly different, which and this is brand new stuff that Clausen and Schulze are currently giving a lecture series on called light condensed sets. So then we restrict our attention to a subclass of profinite spaces, those that are given by a sequential limit of finite sets, and not just any co-filter limit. And they have an equivalent classification as those profinite sets that have countably many Clopen subsets. Or if you want to talk about stone duality, then it just means that the corresponding Boolean algebra is countable. And this category is at least essentially small, and that's good enough. Like then you can take values in small sets and chiefify, and everything works. You're just computing a small colimit. They have exactly the same explicit description. Like you can equip this category of light profinite spaces with coherent topology, and then define light condensed sets as actual sheaves on that category. And this is a much nicer object. Now, this is of course not the same thing as a condensed set, so there are some pros and cons, I guess. But I think for these new foundations to analytic geometry that they are proposing, this turns out to be more convenient. They form a topos, and the theory of so-called solid and liquid modules. As you probably know, the liquid tensor experiments was about these liquid things, and yeah, solid and liquids are just ways to analogs of complete topological abelian groups. And these theories become sort of, I don't know, maybe not nicer, but at least easier in this setting of light condensed sets. But you lose something. You're not generalizing as many topological spaces. So it's defining profinite sets, the light profinite sets. So profinite sets have a basis of Clopens, and since these are countably many Clopens, they're second countable, meaning that they're metrizable, and this means that you're only your functor from topological spaces to light condensed sets is only fully faithful when you restrict to metrizable topological spaces. But that's still quite nice. Okay, so yeah, let's just look at some code. If you want to follow along, here's the name of the Mathlib branch I'm working on. So it depends on a few PRs, so not all of it is on Mathlib master yet, but some of it is. So the name of the branch is just my name _ lean together talk. Yeah. So you can see the code, right? Yeah.
Yes.
Okay. Let's see. So yeah, I start by redefining. I define here a condensed set prime, because condensed set is defined as something slightly different in Mathlib, as a sheaf for the coherent topology on profinite sets valid in type U+1. So let's look at this coherent topology. It's a quite general thing. So it's the Grothendieck topology generated by this coherent coverage, which just consists of finite families. It's a bit hard to read maybe, but it says like finite families, finite effective epi families. It's all about these effective epimorphism, which is a very general categorical concept, but it's sort of an analog of quotient maps in topology. And in when your topological spaces are compact Hausdorff, then quotient map is equivalent to continuous surjection. So it just means surjective in this case. And profinite is just a compact Hausdorff space which is totally disconnected, as I said, and we have a bit of API for profinite sets. It's I mean, here's all the stuff relating it to the category of topological spaces. Then this file as limit proves a limit formula for them. So we can write them as co-filter limits of finite sets, and then the category is closed under limits. So we have this description I mentioned, and yeah, a few other files, some explicit descriptions of limits and so on. Yeah, and okay, so I define my condensed sets as sheaf on the side of profinite sets, but Mathlib defines them as so sheaves on compact household spaces. But we have the equivalence. My condensed set prime is equivalent. We have an equivalence of categories of these sheaf categories. That's quite a non-trivial result, and was worked on a lot during the Copenhagen masterclass. Okay, so if we have a profinite set and a condensed set, we can, let's see. Yeah, so a sheaf is a structure with two fields. X.val is just a pre-sheaf, and we can evaluate it on S. Get a type U plus 1, and then the second field of the structure is the sheaf condition, which I won't go into too much. Now, yeah, so if we look at this light profinite, that's the basic definition is already in Mathlib. So I think Mathlib master only has this basic file, but I've PR'd a few more. So it's a structure with it's more structure than just a profinite set. We have given a diagram of finite sets indexed by, it's a sequential diagram, a limit cone on it, which a cone on it, which is a limit cone. So like it's always enough to give the first and third field. It can infer the cone from the third one, but this is actually quite convenient to be able to access this limit cone directly from the structure. But to be able to prove any results, we need this characterization I mentioned about. Maybe first, importantly, it's essentially small, as you see here. But unfortunately, there was no API for sheafification or essentially small categories. So I'm working on developing that as well. But yeah, there was this characterization in terms of countably many Clopen subsets. That's here. I define a class, just a predicate on profinite sets is light, saying that it has countably many Clopens, and then I prove that, like, given a light profinite set, its underlying profinite set is light, and given a profinite set which is light, you get a light profinite. And then we need some explicit limits to prove that it has this properties required to define this coherent topology. And then we can define light condensed sets. These are not in Mathlib yet either, but PR'd. So it's exactly the same. It's just a sheaf for the coherent topology and light profinite sets. And here it's in type U. The target category has the same universe as the defining site. yeah, so here I'm showing that we can sheafify. Pre-sheaf to sheaf is the sheafification functor, and everything works. Now, if we would try to do the same thing for condensed sets, let's define something called small condensed sets as just sheaves on profinite U valued in type U, and try to sheafify it in the same way, you get an error. So what we have to do is have our pre-sheaf take values in type U plus 1, and then we can sheafify. Okay, we can also talk about condensed abelian groups, of course, just having our sheaves take values in the nicely named category of abelian groups, adcom group cat. And I can do all the same stuff here, and yeah, works the same way. And yeah, light conda is, and it's valued in the lower universe. If you're doing condensed, you have to bump the universe also here. Sheafification works fine because the category of abelian groups has nice properties, and these categories are abelian. We have that as well, both condensed abelian groups and light condensed abelian groups. Okay. Now, so here I'll show a small example about why it's nicer to take values in a lower universe. I mean, not having to bump the universe. So let's check this. So condensed.discrete is just the functor from a category to a category of condensed objects. It's the constant sheaf functor. So yeah, you would like to be able to regard your objects in your category, say sets, as discrete sets in the condensed world, and that's this functor here. Now, let's say we want to study the abelian group of integers as a condensed abelian group. Then we would use this condensed.discrete functor, and it doesn't work because it's expecting an object of type one universe higher. So I mean, you can solve this by doing ulift, but that's only because someone has, added all the algebraic instances for ulift, and yeah, it's not very nice to work with ulift. Here in light condensed, we have exactly the same thing, and then it just works right away because the integers is a term of type so type 0, and here our sheaves are taking values in that category and not type 1. Yeah, I think I'm out of time, so I'll stop here.
Well, thank you very much. Are there any questions? Patrick, you were first.
Hey, hi, thanks. So I got two related questions. So what are your targets in this story? What are you aiming for? And maybe the related question is this going to bring the liquid tensor experiment into Mathlib ultimately once you've redone it in this new framework, or is it not one of your targets?
maybe not exactly the liquid tensor experiment. I'm mostly focusing on the solid theory right now, which is a bit simpler. So yeah, I guess I had one slide left with future work. So the solid theory is an analog of the liquid stuff for like non-Archimedean, right? And we have the definition of solid condensed abelian groups in Mathlib, but it's like completely impossible to do anything, to prove anything for them yet. And in this light setting, that becomes quite a lot easier actually. So that's, I mean, it's still a lot of work, but I think it's more doable to, for example, prove that discrete abelian groups are solid in this setting. Yeah, then I mean, there's this new homology API that should be usable in this setting because there are abelian categories, and it would be fun to also do some condensed cohomology or something like that.
Is the idea that the light theory will just replace the solid, the original theory?
I mean, for Destiny Peters applications, I think so, yeah. But I mean, the old condensed stuff is still there, and who knows? Maybe it turns out that there are some applications where you actually have to use the old ones and not the light ones. I don't know.
Time will tell. So Johan,
yeah, I mean, it's all really new. So
yeah. I should say this is the second talk where we've heard about sort of 2023 mathematics. Johan, go ahead.
Yeah, thanks for the talk. So I was wondering, one crucial object in the light solid theory is this object P. I guess you know what I'm talking about, this Z joint and infinity modulo infinity. And it's internally projective, which is a very important feature of this object. Yeah. Do you have any idea how far you are from formalizing that? Because it seems like most of the stuff is in place, and it might actually be quite approachable.
Yeah, I think it's approachable. I started working on it on a branch, but then I haven't had time to look at it for a while. It's so to explain to everyone else like this, there's this one object in light profinite set which is the sort of classifies null sequences in light condensed abelian groups, and it's the 1-point compactification of the natural numbers. Yeah, I mean, I don't think we have everything we need to formalize it. It's just that we have to do it. I don't know exactly the best way to do it, but yeah, I'm sure we'll find something.
Because then we might actually get an example of an analytic ring in Leap, which would be pretty cool.
Yeah.
Okay, so last question. Do you have about 40 seconds? Adam, go ahead.
40 seconds, yeah. Thanks. Yeah, good talk. Thanks. I guess my question is about, it's kind of related to Johan's question, but if I remember correctly, so you mentioned one kind of defect of light condensed sets, that they don't capture as many topological spaces, but there's another defect that not all the AB axioms that hold for condensed abelian groups hold for light condensed abelian groups, right?
Yeah.
I think like one of them, only countable products are exact or something like this, right?
Yes. Yeah.
And I would imagine that proving these AB axioms or these kind of weaker AB axioms for light condensed abelian groups will be much more difficult. And if I understand correctly, these are going to be required for proving that this P object is internally projective. So I guess my question was whether you've given any thought to how to approach these AB axioms for light condensed abelian groups.
You can answer quickly, that would be great.
Yeah, I haven't thought about it a lot, but it's true that it's going to be more difficult. Like, yeah, so I guess it's related to the fact that like light profinite sets, like an easier but similar problem is to prove that light profinite sets have all countable limits or something like that. And like profinite sets have all limits for abstract nonsense reasons, but light profinite sets, you have to do some work to prove the existence of limits.
So
But yeah,
plenty
no,
of things
I
that
haven't
need
thought
doing.
about the AB axioms.
Plenty of things to do. Yeah.
Yeah. Okay. Great. So homework. Okay.
But
So
I
thank you very
guess,
much. We will return in 14 minutes for the final session of the day, and let's now move over to